Hi everyone, welcome to this video where today we're going to talk about rational functions, what an asymptote is, and how to figure out the excluded values. So let's take a look. Now, a rational function is a function that is in the form of this equation. It's y equals some number a over x minus h plus k. Now, it's been a while, but we've seen a, h, and k a lot. We know h and k are the vertex of a parabola. We know hk is the vertex of an absolute value function. We even saw h and k in our radical functions. This letter A, has always controlled the shape of things. So if A is positive, the graph is facing upwards. If the A is negative, the graph is facing downwards. If it's a number that's greater than 1, it's making the graph wider. If A is a value that's between 0 and 1, it always makes a graph more narrow or steep. And the same thing is basically going to be happening here. But this is very different because we've never had x be in the denominator before in any kind of equation we've dealt with. Now, an excluded value means this is the first thing we're going to be learning. An excluded value is a value of x that it cannot be, because if x was that value, then the denominator would be 0. And we know anything that's 0 in a denominator is undefined. We can't have that. So here it says, because division is undefined by 0, any value of a variable that results in a denominator of 0 must be excluded from the domain of that variable. Now, I know this probably doesn't sound like much to us just yet, but let's take a look at this really basic function. It says y is equal to 5 divided by x minus 2. So here, if I have this function and I say to you, what's the excluded value? I'm basically saying to you, what's the value that x can't be? Because if x was that value, the denominator would be 0 and it would be impossible. It couldn't even be something we could calculate. So notice we really care about the denominator. We don't care at all about the numerator. The numerator can basically be whatever it wants. But this denominator, so in order to figure out what x can't be, I want to set the denominator actually equal to 0. What x value would make that become 0? Well, solving this, if I add 2 on both sides, we're going to see that it's 2. 2 is the excluded value. X can be any number in the world. It could be 5, it could be 4, it could be 3, but it can't be 2. Because if I plug in any of those other numbers, I'm going to get a denominator, a good denominator, and I could do 5 divided by it. But if I plug in a 2, 2 minus 2 is 0, can't have a 0 as a denominator, and so it's called the excluded value. X can be any value except for 2. You could plug in a positive number there, a negative number, a fraction, a decimal. It would all give you some kind of value after you do 5 divided by that amount. But if you plug a 2 in, it's going to be no good. Okay, so we're going to take a look at that first, calculating excluded values. So let me just get my screen put together for us. Okay, some of these are going to be really, really quick, and some of them we're going to have to do a little bit of math, and you can see by those blobs over there. So if I give you this function, y equals 4 over x, the excluded value would be what x can't be, because if it was that, it would make the denominator 0. Well, here, when the denominator is just x, the excluded value is really easy. It's 0. X can be any number in the world except for 0. Here, y equals 2 over x plus 3. Well, what value of x would turn this denominator into 0? It would be negative 3. So the excluded value is negative 3. X can be any number in the world in this equation except for negative 3. 7x. Well, this one's kind of like when there's just an x there. If you were to set 7x equal to 0, you end up still getting 0. So 0 is the excluded value. X can be any number in the world except for 0. And remember, we don't care about the numerator, we just care about the denominator. Next one, x plus 3 over x minus 5. The only value x cannot be here would be if x minus 5 was equal to 0. The excluded value is simply 5. Next one, if I do the same process and I set this denominator equal to 0, notice that's what I'm really doing. I'm just setting the denominator equal to 0. And I add 15 on both sides, divide by 5, I end up getting x equals 3. Because think about it, 5 times 3 is 15. 15 minus 15 is 0. That's definitely my excluded value. 2x minus 1, if I set that equal to 0, add 1, divide by 2, my excluded value is 1/2. So x can be any number in the world except for 1/2. That's the excluded value. Now these next two, the denominator is a trinomial. It's been a while since we've seen trinomials, but remember, we can factor them. So if I set this denominator equal to 0 and I go to factor, remember, step 1 in solving a polynomial equation, set the equation equal to 0. Step 2, factor. What factor pair of 3 adds up to give you 4? Well, the only way to multiply to get 3 is a 1 and a 3. What kind of 1 and what kind of 3 do we need to add up to get a positive 4? They would both be positive. Now let's see what else we remember. If it's x plus 1, what do you remember the solution being? -1. If it's x plus 3, what do you remember the solution being? -3. X can't be -1, x can't be -3. This one actually has 2 excluded values. Over here, if I set this denominator equal to 0, this is a binomial. It's a difference of squares. It's a perfect square minus a perfect square. So we factor this out as x plus 5, x minus 5. Our first excluded value is -5. Our second excluded value is +5. So these over here only had 1 excluded value, but these last two problems actually had 2 excluded values, and they definitely involve some factoring. Okay, next skill that we have to learn about is an asymptote. Everyone say asymptote. Asymptote. Yes, asymptote. An asymptote is a line that the graph of the function approaches. It's really, really close to it. Now, we've learned about asymptotes before, but we never really actually spoke about them yet formally. When we were doing exponential graphs and we had a graph of a decay, I talked to you about how the graph gets really, really close to the x-axis, but it never actually touches it. This is the asymptote. The line that a graph seems to curve towards and approach but never actually touch is the asymptote. You can have a horizontal asymptote. You can also have a vertical asymptote, and we're going to have both. So in that function formula that I showed you, y equals a over x minus h plus k, k is the y value for the horizontal asymptote. Remember, any horizontal line is actually y equals this, right? So this could be y equals 2. This is y equals 3, y equals 4. The h value for x minus h, whatever that h value is, that's your x value, which is your vertical asymptote. So remember, this would be 0, this would be 1, this would be 2, this would be -1, this would be -2. So that's your vertical asymptote. Now, if I gave you this graph, a graph of something you've never seen before, you've never seen a graph that looks like this yet. You've only had one curve ever, but I'm going to show you what this graph actually looks like. We have a vertical asymptote and we have a horizontal asymptote. Now, x is always our vertical asymptote. The asymptote is where it cuts the graph, basically making that vertical line that both curves are trying to approach. This is the vertical asymptote. It's a vertical line that's kind of slicing right in between where these graphs are approaching it. And both of those graphs are actually for the same function. So if I was to take a look at this, okay, and I have this equation, which actually looks like this graph, this double graph, this is my vertical asymptote, and the asymptote is at x equals -2. I know that's pretty light, so I'm going to draw over it. Okay, my horizontal asymptote would be the horizontal line that I see the graphs also kind of getting close to but never touching. That's at y equals 1. Okay, those are my asymptotes. So x equals -2 is this line here, and then y equals 1 is this line here. And those curves are going to approach it but never actually touch that line. That's what an asymptote is. So let's take a look at the next set of problems. I've got 4 graphs that we're going to be actually creating mildly. We're not going to be super, super nutty with the points, but we're going to make them approximately. So the first thing I want to actually do with you is I want us to label the asymptotes. I'm going to give you this graph, we're going to remember that the formula is y equals a over x minus h plus k. So here, h is the vertical asymptote. So that's going through my x-axis. So here if it says x minus 2 and the formula is x minus h, then that means my h value for my horizontal asymptote is at 2. I'm going to go ahead and draw that. So at x equals 2, it would be this line here. Okay, this next one, if it says x plus 2, well, that means that the h value that got plugged in was actually negative 2, because x minus negative 2 would turn it into that positive 2. And so I'm going to then draw that vertical asymptote here. I'm going to do all the vertical asymptotes first. In this next one, I don't see x minus anything in the denominator, so that actually means that my vertical asymptote is at 0. And an x vertical asymptote at 0 is actually just the y-axis. And then the same thing for this last one. I just see 0 in I just see x. I don't see any minus or plus h, any h values. So it's just going to be the y-axis. Now let's look at the y value. The y-asymptote is your horizontal, and that's just the k value here at the end. So if you see plus 1, that means the y value is 1. Here's where y is at 1. Next one, negative 3. So my horizontal asymptote for my y value is at negative 3. Next one, negative 2. So my y-axis at negative 2 would be my next asymptote. And the last one is at positive 3. And I'm going to create that asymptote. Awesome. Now I want to briefly show you what these graphs would actually look like. So they're actually curves in opposite quadrants created by the asymptotes. So this is interesting. A possible point that I could plug in here for x, let's say, is 3. So let's say I plugged in an x value of 3. 3 minus 2 is 1. 1 divided by 1 is 1, plus 1 is 2. So a point on this graph is 3, 2. So when I plug in a 3 for x, I get 2 as my y. So 3, 2. Look at where that point sits. It's pretty interesting. That point is actually the point that's going to say, hey, my curves are going to approach those asymptotes, but they're not actually going to touch them. And then the other part of that graph is actually in the diagonal section to that. Another x value I could plug in is, let's say, negative 1. No, I'm actually going to plug in a positive 1 instead. My apologies. Positive 1. Ready? So if I plugged in a 1 here, just erase that out. 1 minus 2 is negative 1. 1 divided by negative 1 is negative 1. Negative 1 plus 1 is 0. So 1, 0, which is actually here, notice it's perfectly diagonal, would actually be where the other curve is. Pretty interesting. Let's look at this next one. If I went ahead and I plugged in a point of negative 2. So actually, I can't plug in a negative 2. Why? Because negative 2 plus 2 is 0. Can't have a denominator of 0. So you just saw me almost mess that one up. Let's plug in a negative 1. All right, so negative 1 plus 2 is 1. 1 divided by 1 is 1. 1 minus 3 is negative 2. So negative 1, negative 2. This is the curve of the graph. It goes to that point and touches it, and I think we can skip the other half, but guess what? The other part of the graph is going to be there. Same idea here. A value that actually divides by 3 is 3. So if I plug in a 3 for x, 3 divided by 3 is 1. 1 minus 2 is negative 1. So 3, negative 1, this point. Now don't kind of get this mixed up. It's not going to curve from here, because think about another number that divides nicely by 3. How about 1? 3 divided by 1 is 3. 3 minus 2 is 1. So 1, 1 is actually the other point, and it curves out this way. And for an a value of 3, it makes the curve like kind of steeper like that, not as wide. Just like the a value did that for parabolas and things like that. Also notice, if the a value is 1, look, from the center of where the asymptotes meet, it's out 1, up 1. If the value is 3 for the a, from where they intersect, it's out 1, up 3. It's not a coincidence. Last one. A number that divides by 2, let's say, is 1. So if I plug in a 1, 2 divided by 1 is 2. 2 plus 3 is 5. So 1, 5 is definitely a point. Another number that divides by 2 is 2. 2 divided by 2 is 1. 1 plus 3 is 4. 2, 4. Do you notice also from the intersection it goes out 1, up 2? Because look, the a value is 2. So if you are making that connection, that's pretty good. And then I'm going to have the symmetric curve on the other side, always diagonal from it. Oh, and I forgot this one here. So out 3 units, out 3 units, 1, 2, 3, and make that curve. Terrible, terrible graph. Thank you so much for watching. I hope this was helpful for you. Bye.